Here's a question that sounds simple until you try to actually answer it. Astronomers have known for a century that the universe is expanding. So why is that expansion speeding up instead of slowing down, the way gravity should demand? The clue that cracked this mystery open came from an exploding star in a galaxy billions of light years away, whose light is only reaching Earth now, carrying evidence that empty space isn't behaving the way anyone expected. Astronomers know roughly how bright an explosion like that should look from here, and this one looked too faint, as if space had stretched more during the light's long journey than gravity alone could explain. That single mismatch, repeated across dozens of similar explosions, exposed one of the strangest facts in modern science. Cosmic expansion isn't slowing down at all, it's accelerating. Scientists named the unknown cause dark energy, though the name is more honest about our ignorance than about any actual substance, since nobody has ever collected it in a detector or isolated so much as a trace of it in a lab. Its existence is inferred entirely from its effects, from what billions of galaxies are doing across the largest scales in the universe, patterns that ordinary matter alone can't account for. To understand why any of this counted as a surprise, it helps to drop the common image of galaxies exploding outward through some pre-existing emptiness. The universe expands because the distances built into space itself keep growing, carrying sufficiently distant galaxies farther apart, even though those galaxies aren't moving through space in any ordinary sense. Think of raisins baked into a loaf of rising dough. No single raisin propels itself away from the others, yet the dough between every pair of raisins expands, so every distance grows right along with it. Gravity works against that expansion, since matter pulls on matter, which is why cosmologists spent decades assuming the universe should be expanding more and more slowly after the violence of its birth. Depending on how much matter the universe actually contained, gravity might eventually stop the expansion and reverse it, or simply slow it down forever without ever quite winning. Either way, deceleration was the obvious expectation, because nothing in ordinary matter provides any kind of sustained cosmic push. By the 1990s, two independent research teams set out to finally measure exactly how much that expansion was decelerating, using a class of explosion bright enough to be seen across billions of light years, type Ia supernovae. These supernovae aren't perfectly identical to one another, but their light curves can be calibrated well enough to work as remarkably reliable distance markers. Comparing how bright one of these explosions actually appears against how bright it should appear lets astronomers calculate exactly how far its light has traveled to reach us. Splitting that same light into a spectrum reveals its redshift, which tells them how much the universe itself expanded while the light was en route. Put distance and redshift together across dozens of supernovae, and ancient explosions turn into markers along a timeline, letting researchers reconstruct how fast the universe was expanding at different moments in its past. Both teams expected that timeline to show a universe that once expanded faster and had been gradually losing momentum ever since. In 1998, the data showed almost the opposite. The explosions looked dimmer and sat farther away than a slowing universe could explain, meaning expansion had actually sped up starting several billion years earlier. Follow-up observations using supernovae and several other independent methods only strengthened that conclusion, and the discovery eventually earned the 2011 Nobel Prize in Physics. None of this means some mysterious wind is pushing galaxies through space, and it doesn't mean the solar system, Earth, or the atoms in your body are quietly being pulled apart. On small scales, gravity and electromagnetism hold matter together far too strongly for this effect to compete. The Milky Way isn't expanding internally, Earth isn't swelling along with the cosmos, and a ruler left on a table won't be any longer tomorrow. Dark energy only becomes important across immense stretches of mostly empty space, where matter is spread thin enough that the cumulative behavior of space itself starts to dominate. That scale dependence is exactly how something practically undetectable in any laboratory ends up controlling the long-term fate of the entire cosmos. According to the standard model of cosmology, dark energy makes up roughly 2/3 of the universe's total energy budget, with dark matter and ordinary matter splitting most of what's left. That figure can make it sound like scientists weighed some hidden fluid directly, but really it comes from fitting a mathematical model to several completely independent sets of observations at once. The cosmic microwave background preserves conditions from the infant universe. Galaxy clustering records how structure formed over billions of years, and supernovae reveal how expansion itself changed more recently. Line those three records up, and a universe built from matter alone simply fails to match the geometry, expansion history, and structure astronomers actually see out there. So either something else is influencing the equations, or the equations themselves are missing a piece. The simplest fix is something Einstein himself had already written into general relativity decades earlier: the cosmological constant, represented by the Greek letter lambda. Unlike matter, which thins out as space expands, lambda keeps exactly the same energy density inside every newly enlarged volume of space. Picture doubling the size of a box. The amount of matter inside stays the same, so its density falls, but lambda's density fills the extra space without thinning out at all. That doesn't break energy conservation in any everyday sense, mainly because energy in an expanding universe can't always be pinned down globally the way it can inside a sealed lab. General relativity ties the curvature of space-time not just to energy density but to pressure as well, and while ordinary matter has almost no pressure on cosmic scales, lambda behaves as if it carries a large negative pressure. Negative pressure sounds like suction, which is a little misleading, since dark energy isn't dragging galaxies towards some distant point in space. What's really happening is that its particular combination of density and pressure changes how the scale of the universe evolves over time, and that shift is what allows expansion to accelerate. In the equations of cosmology, pressure itself gravitates, and sufficiently negative pressure works against the usual decelerating pull of matter instead of adding to it. This is one of the places where intuition built from watching apples fall on Earth simply stops working, because general relativity treats gravity as a behavior of space-time itself rather than a straightforward pull between objects. Lambda fits current observations remarkably well and forms the backbone of the standard lambda CDM model, where dark energy stays perfectly smooth, never clumps into galaxies, and never changes as the universe grows. Calling that model simple doesn't mean physicists actually understand why lambda exists, or why it happens to carry the specific, tiny value astronomers measure. Quantum field theory suggests empty space isn't truly empty in the first place, since fields remain present even in regions with zero particles floating around. Those fields carry their own vacuum energy, which makes it tempting to just declare the cosmological constant equal to the energy of the quantum vacuum and call it solved. Straightforward calculations of that vacuum energy, though, come out catastrophically larger than the tiny value astronomers actually observe in the real universe. Exactly how large the mismatch looks depends on how the calculation gets framed, but the core problem stays severe no matter what. Known physics simply doesn't predict a number this small on its own. If the vacuum really did gravitate at anything close to the strength naive calculations suggest, space would have torn itself apart so violently that stars, galaxies, or any stable structure could never have formed at all. Some unknown mechanism has to cancel out almost all of that expected contribution while leaving behind just barely enough to dominate the universe we see today. That's the cosmological constant problem, a genuine collision between quantum theory, gravity, and observation, not some minor gap waiting on one better measurement to close it. Solving even that wouldn't finish the story, because matter and dark energy trade places an importance as the universe ages. Matter density drops as volume grows, while lambda's density stays fixed, so the early universe was overwhelmingly dominated by matter and radiation rather than dark energy. Only relatively recently did the two densities become comparable, letting dark energy finally overtake matter and start accelerating cosmic expansion. That means humans happen to exist during the one narrow stretch of cosmic history when both components are important enough to even notice, which some physicists find profound and others treat as nothing more than a selection effect. Maybe observers can only ever arise during a fairly specific set of cosmic conditions, which would make our timing far less mysterious than it first appears. Then again, lambda's value might simply be fixed by laws nobody has discovered yet, with no real freedom for it to have ever come out differently. Or maybe dark energy isn't constant at all. That last possibility opens the door to quintessence, a hypothetical field that shifts gradually as the universe ages instead of freezing at one fixed value forever. A field like that could carry different density and pressure combinations at different points in cosmic history, letting acceleration strengthen, weaken, start later, or even reverse somewhere down the line. Physicists track this behavior with a single number called W, the ratio between dark energy's pressure and its density. A true cosmological constant sits at exactly W equals -1. Values above that resemble typical quintessence behavior, while values below it describe a stranger, more extreme case researchers call phantom energy. These are useful labels rather than confirmed substances, and models with very different underlying physics can sometimes produce nearly identical observational signatures. A confirmed shift away from W equals -1 would be genuinely revolutionary, turning dark energy from a fixed number sitting in an equation into evidence of an actual new field or interaction at work. It might even end up connecting today's acceleration to other chapters of cosmic history, although no established theory currently makes that link. Push further out, and the proposals get stranger still. Dark energy trading energy back and forth with dark matter, leaking in from extra dimensions or emerging from large-scale structure that a perfectly smooth model simply fails to capture. Whatever the proposal, it faces one brutal test. Explain the acceleration without wrecking general relativity's many other successful predictions, from galaxy formation to gravitational lensing to the precise motion of planets in our own solar system. A theory can look elegant sitting on paper and still fail completely, since the universe leaves overlapping records of its history scattered across far too many independent forms to fool all of them at once. There's an even more radical possibility waiting in the wings. Maybe dark energy isn't a substance in the universe at all. General relativity has passed demanding tests for more than a century, but almost all of those tests involve stars, planets, and black holes, which is to say relatively local, well-behaved gravity. Stretch the distances out to billions of light years, and Einstein's equations might quietly behave a little differently than assumed, producing something that looks exactly like acceleration without requiring any separate dark energy ingredient at all. The trouble is that tweaking gravity's rules tends to also change how matter clumps together, how light bends around mass, and how cosmic structure grows over time, so it's rarely a clean, isolated fix. That's why astronomers try to measure all of it simultaneously, since a genuinely new form of energy and a genuinely new law of gravity tend to leave different fingerprints once you look past expansion on its own. Supernovae remain one of the main tools here, acting as calibrated beacons scattered across many different chapters of cosmic history. A second method leans on baryon acoustic oscillations, a faint rhythmic pattern left behind by sound waves rippling through the hot plasma that filled the infant universe. Once the universe cooled down, that rhythm froze into a preferred spacing between galaxies, essentially stamping a fossil ruler across the entire sky. Because the ruler's original length can be calculated directly from first principles, its apparent size at different redshifts reveals exactly how cosmic distances have stretched over billions of years. The Dark Energy Spectroscopic Instrument, DESI, has been mapping the redshifts of millions of galaxies and quasars, building a three-dimensional atlas that spans much of cosmic history. Its most recent analysis, released in 2024, drew on nearly 15 million well-measured galaxies and quasars to track expansion across roughly 11 billion years. Taken entirely on its own, DESI's data still lines up fine with a plain, unchanging cosmological constant, which is an important check against getting carried away too quickly. Combine those numbers with certain supernova catalogs, cosmic microwave background data, and weak lensing surveys though, and the best fit model starts leaning toward dark energy that changes over time instead. Depending on exactly which datasets get combined, that preference ranges from mildly intriguing to fairly strong, but it hasn't crossed the line cosmologists consider an actual discovery. That distinction matters because cosmology routinely tries to pull a faint signal out of enormous datasets, and hidden calibration quirks or correlated errors can easily end up masquerading as real physics. Different supernova compilations don't even fully agree with each other, and a model with more moving parts will always find it easier to fit small irregularities than a rigid one will. Cosmology's history is full of exciting statistical hints that quietly dissolved once more data exposed the noise, bias, or underestimated uncertainty hiding underneath them. So the DESI hint sits in a genuinely uncomfortable spot, not proof that dark energy evolves, but not something safe to wave away either. A pressure point worth testing from every possible direction. Europe's Euclid mission is built for exactly that kind of stress test, mapping the shapes, distances, and distribution of billions of galaxies across a huge slice of the sky. By tracking weak gravitational lensing, the way foreground mass subtly warps the light from galaxies behind it, Euclid can trace where matter actually sits, dark matter included, and how efficiently gravity assembled structure over billions of years. If the story told by expansion and the story told by structure growth line up, the plain cosmological constant becomes that much harder to dislodge. If instead they disagree in some consistent, repeatable way, that mismatch could point toward evolving dark energy, modified gravity, or a flaw still hiding somewhere inside the measurements themselves. No upcoming survey is going to detect dark energy directly, the way you'd spot a particle in a detector. Instead, each one narrows the ring of possible explanations a little further, from every direction at once. And the answer decides more than just today's expansion rate, because whatever dark energy turns out to be also decides how the universe eventually ends. Suppose it really is a true, unchanging cosmological constant. Acceleration keeps building without any limit, and everything outside our own gravitationally bound patch of galaxies recedes faster and faster forever. Give that scenario enough time, and distant galaxies eventually cross a horizon their light can never reach us from again, vanishing not because they physically moved away, but because the space between us stretched faster than light could ever cross it. Some unimaginably distant future version of the Milky Way's night sky would look darker and emptier than ours does now, even as countless galaxies kept existing quietly just beyond view. The tightly bound galaxies of our own local group would likely stick around regardless, while the visible evidence of the wider, expanding cosmos slowly faded out of sight entirely. That's just one possible ending, and the alternatives look very different. Dark energy could just as easily weaken over time, stalling acceleration and handing the future back to ordinary matter and gravity. Or its value could tip negative and let expansion eventually collapse back on itself, though nothing currently observed forces that outcome. Push the numbers toward the opposite extreme, a phantom scenario where dark energy actually grows stronger with time and expansion could eventually overpower gravity even inside galaxies and solar systems, ripping apart bound structure entirely in what researchers call the Big Rip. That's a mathematically valid ending in some models, not a forecast that anything currently observed actually demands. Other proposals let dark energy decay into something else, oscillate, or settle into a new stable value altogether, meaning the true final chapter of the universe still depends on physics nobody has identified yet. So the mystery can't really be flattened down too. Dark energy pushes galaxies apart because that's the headline, not the explanation. What astronomers can actually say with confidence is narrower than that. Cosmic expansion is accelerating, and the simplest model that fits everything represents the cause as a small, positive cosmological constant. Whether that constant is vacuum energy, evidence of a slowly shifting field, a sign that gravity itself needs revising, or something stranger hiding behind an approximation, nobody currently knows. Dark energy might turn out to be a genuinely new ingredient of nature, or it might be the first real crack showing exactly where general relativity and quantum theory quietly fail to fit together. Its almost perfect smoothness is one clue, its impossibly tiny measured density is another, and the recent hints that it might be shifting over time make a third, though none of them adds up to a full answer just yet. Real progress here comes from stacking independent cosmic records against each other, rather than betting everything on one spectacular observation. Supernova measure brightness and distance, galaxy surveys hand over a cosmic ruler, lensing traces where mass actually sits, and the cosmic microwave background anchors the whole timeline back to its earliest conditions. Each method carries its own weak points, which is exactly why agreement between them means so much, and disagreement between them can be just as scientifically valuable. The work ahead isn't simply gathering more galaxies, it's understanding instruments, calibration, contamination, and mathematical assumptions closely enough that no subtle cosmic signal can hide behind them unnoticed. That patience matters because whatever answer eventually wins reaches far past astronomy, straight into open questions about matter, space, time, and gravity itself. A confirmed shift away from W=-1 would force physicists to explain exactly what's evolving, why it's so unbelievably faint, and how it managed to hide from every local experiment ever run. A confirmed, truly constant lambda would leave behind an equally uncomfortable question of its own: why the vacuum carries this exact, extraordinarily small gravitational effect instead of an enormous one, or none at all. Either outcome counts as a genuine discovery, because even the simplest possible answer still leaves one of the deepest unsolved problems in physics standing exactly where it was. The phrase dark energy makes the whole thing sound like some hidden fuel tank waiting to be found somewhere out between the galaxies. In reality, it names a pattern stretched across the universe's entire expansion history, one that only becomes visible once enough different kinds of evidence get laid side by side. All of this traces back to a single distant supernova whose light arrived just a little fainter than expected, carrying no message beyond the sheer distance it had crossed to reach us. Buried inside that faintness, though, was a quiet warning that our picture of empty space had been incomplete the whole time. Space itself might carry an almost perfectly constant energy, Or it might be shaped by a field that's still slowly changing, or gravity might simply behave differently across the very largest distances we can measure. Until those three possibilities get properly separated, the single largest component of the modern universe stays something we can measure with real precision, yet still can't fully explain. Dark energy, in the end, isn't the answer to why the universe accelerates. It's the name of the question, the acceleration left behind. And the ancient light still crossing that expanding darkness right now may be the very thing that finally tells us what empty space is actually capable of.